Dr. Smarr.
We're back again.
Deja vu all over again. How are you?
I'm good.
Good. Nice to have you here
Yeah.
at your show.
It's
Old home week.
It's developing. So, one of the things that I was going to start off with is, where did this idea of once in a century thing come from? And just one of the examples is computing. When I started programming 1966, the first million floating point operations per second computer had happened, and that was actually called the first supercomputer. That was 50 years ago. 1 million of those is a teraflop, and 1 million of those is an exaflop. Mm-hmm. And that's what we've seen in this last 50 years. And the real question is it just going to be the same thing all over again? I mean, when I bought my first Cray 2, that was a gigaflop, that was a billion floats. ASCII Red came into Los Alamos, late 90s, that was a teraflop. First petaflop, IBM. And now we're having an executive order from, let's see, go ahead and have the slides. A few years ago from President Obama, which, happened on his watch, but the main thing is that this has been a zillion technical experts and a zillion studies leading toward this, of doing an exascale machine. And an exascale is, like I said, is basically 1 million teraflops, or about 100 million times as fast as your smartphone. But will it be the same this time around? And I think it'll be very different.
In what way?
Well, let's see. Do I have a clicker? Yeah. This idea that the brain is our biologically evolved information systems will become a new model for computer architecture is something I've been talking about for 15 years. But as you know, we had Dharmendra Mota here last year in IBM, and his work in 2011 showed that you could simulate the behavior of a brain. And these charts take you back to the gigaflop, the Cray 2 I bought, all the way up through the exascale. And what you can see is that where he was doing it, you were doing something like a few percent of the human brain and 1/80th of real time. With the exascale, it becomes 100% of the complexity of a human brain in real time. Mm-hmm. And we've known this for 15 years. I get charts like this 15 years ago. But 2020 seemed a long way away in 22,000. Mm-hmm. 3 years. Mm-hmm. And in fact, the first exascale machine was just announced a few weeks ago. The Aurora will go into Argonne, and that'll be an Intel Cray machine. And then Nvidia and IBM are also working on a similar one. That's 2021. Mm-hmm. So the only difference is you're running, I don't know, Mark, maybe 80 watts right now to run your brain. And this thing will try to take 80 megawatts. So somehow biology has found out a way to be 1 million times more energy efficient. You can't throw away a factor of 1 million. And so more and more I see this brain-inspired, which is a bad word, just like innovation, that really the time has come.
Mm-hmm. As we just saw in the last presentation, and I was commenting on actually Dharmendra's chip, but when people talk about things that are brain today,
yeah.
And I'm going to leave out the Allen Institute for a moment, but
yeah.
It's so remarkably less like the brain than it sounds. So I think what they're saying, what they mean when they say something was brain inspired is inspired. They found something, anything at all, on the floor mm-hmm. that had to do with how the brain works, and they incorporated that into a chip or a function, and that's called brain inspired.
Right.
But people, I think, who are not aware of the details of that technology think that it's like the brain. And it's nothing like the brain.
No, but it's also nothing like we've built computers for the last 60 years.
Right.
And this is Nonvon Neumann and one of his first machines. And this sort of a jargon word, von Neumann architecture, is the fundamental idea that you have that you store the program and the data in a storage device with a processing unit. And this looks like, well, what else would you do? And that's really what we've done for, 60 years.
Right.
But people I really respect, like Horst Simon, who's the deputy director for research at Lawrence Berkeley National Lab, and who I've worked with for 25 years in this field, he says that somehow these new so say something is non-von Neumann is doesn't tell you what it is, except it's different than what we've thought about. And he believes we're going to need these, and the reason is because the huge potential in pattern recognition and streaming data analysis. So you may have noticed back when we were talking about the executive order, the big difference in the Exascale is that this we are required to make data analytic computing, the sort of visual computing you're seeing, work as well as solving partial differential equations, which is what we've been doing ever since World War II. Well, when you change the design spec at that fundamental level, and you're going to say the stuff Chris Johnson and you've been showing you now for years, that's got to happen in this computer the same way.
Right.
You can't just use the same old, run it up one more time,
right.
increase the clock speed or something.
Right. You can't just add more servers to AWS and be, yeah.
Exactly. And so that's what Horst has been talking about. And so naturally enough, you brought this, Mark, to the FiRe folks several years ago. This is 2015. That's Professor Ken Kreitz-Delgado, who's one of the experts at UC San Diego in machine learning, all the different aspects of machine learning, announcing the pattern recognition lab that I have, basically co-birthed. But the idea is to take all these different algorithms of machine learning, a number of which have been, like neural nets, have been derived from observing how, brains learn, but including all kinds of not just GPUs and CPUs, which are, by the way, both von Neumann architecture, but these non-von Neumann. And the fundamental concept here, and this is way oversimplified, it's not really the way the brain works, I got all that, right? But fundamentally, we've done this logic, arithmetic way of, it goes back to Babbage, right?
Yeah.
And yet there's this whole way that humans actually interact with the world, which is intuitive, visual, pictorial computing that we barely understand in the biological systems. But if we could bring that together into the design of post-exascale machines, it would be a radical, once-in-a-century shift.
So one of the things we just heard, I think, was the visualizations and the abstraction of the patterns inside those things, and then looking at the differences.
Right.
And Babbage's original machine was called the difference engine.
Yes, it was.
I think that's kind of cool.
Yes.
And so we're going back to the future here a little bit.
Pretty much.
And this has nothing to do with nothing, but I was reading about him the other day, and his computer design number 2 took 153 years to build, and it was built 2003 or 4 in Britain, and had 8,000 moving mechanical parts, and it worked. It was the first time it was built. So when we finish this week, we don't want to wait 153 years to actually build that thing. We want to build
even with Lee Hood's amazing both personal example of longevity and he's sharper than ever, and I've worked with him 25 years. Yeah, we can't wait that
We can't
long.
wait that long. All right, so keep us going here. We have
Okay.
left brain, right brain.
Okay, so first of all, I wanted to, as long as we're doing historical quotes, von Neumann himself, probably as early as the 50s, said, with the incredible speed of digital computers, which at that time were up to maybe 1 floating point operation per second, the human being cannot keep up with this prodigious flow of data. Therefore, we need to take the output of the computer, and before we present it to the human, put it through a visualization device, the oscilloscope. And then the human will look at the visual time-changing patterns on the oscilloscope, and the eye-brain, I'm elaborating this, he didn't say all these words, but basically the eye-brain system will now have the natural way for it to interface with the world. So, 60 years later, Mark, here you are.
Good to go.
So these ideas have been around for a long time, but I think the fundamental things, there's 2 things I would say basically that have fundamentally changed. One is we are really getting to reverse engineering the brain, and this is from Cal IT2, one of our 64 million pixel walls, and this is a colleague of Chris Johnson, Mark Ellisman's, and this is at least 10 years old. This is a confocal light microscope where the robot goes like this across the sample of the rat cerebellum, which is about half the size of your little fingernail. And you can see in this the detailed large-scale structure of actually how all of those neurons in your brain are put together. And if you zoom in, those little blue dots in the center of the light blue, that's the DNA, stained DNA in the nucleus of the Purkinje neurons, and that all that sort of forest-looking stuff where things overlap, that's the overlapping synaptic conjunctions that makes the brain so not like a von Neumann machine. Now, this is not just 2D, it's actually 3D in depth, but there are extraordinary efforts now that are literally reverse engineering all of the connections in the brain, visualizing those, and beginning to understand a tiny, tiny bit about how this thing works.
So let's do a little dive here.
Yeah.
When you look at this, or when you look at a detailed picture of neurons and how they're structured, one of the main differences that leap out are every single one of those is different. Not like chips.
Right.
And then where the synapses occur and where the bodies, the dendritic bodies are located, is anything but obvious. It's as though there's a conversation that goes on during the creation of the brain, which tells each nerve where it wants to put the next thing.
Absolutely, it's
And so
evolved.
It's a truly an information flow-based
And in
conversation.
fact, the brain gets rid of a whole bunch of
It
these
prunes-
interconnections,
it
prunes the tree, as you know, in the first few years of life, and that all comes, as Piaget taught us long ago, the Swiss scientist who watched how children learn, that it's only through the interaction with the environment that the brain evolves itself, prunes itself, and optimizes itself for interacting largely visually and with other things, with the real world.
And we were wrong. We thought for a long time that it's just when you're a kid. But in fact, what really happens is the brain remains plastic throughout your life.
Right.
And there's a book by Ivan Deutsch about this. But so when there's an injury or so forth, there are literally ways, often visual, which allow the brain to retain its plasticity or even accelerate its plasticity and regain functionalities that were lost through injury or something else. So that conversation of where to grow and where to assign functions never stops.
Well, and there's a huge redundancy. I don't know, some of you have probably seen the PBS special on the brain, and I was on a stage with the guy who, is the person who takes you through all that, and what he has done is got a whole new program of taking what you just said to an extreme, where you can see with your tongue, where
you can put a little pad on your tongue.
Yeah.
Yeah.
And you can
or on your back.
And you basically retrain the brain to do what the visual cortex is mostly set up to
This
do.
is for people who've been blinded.
Yeah.
You put a pad on your tongue with little tingly things.
Yeah.
And your tongue becomes your eyes.
And then he has all these vests that
Yes,
have
okay.
actuators and so forth, and you begin to interact with the world and retrain this new, basically, it's basically that the brain is set up that you can plug in any new sensory input device, and it will plastically figure out how to take that sense data
Right.
and interpret it in terms of
Right.
what's out there.
So I think that the takeaway from this part of our conversation is, unlike the way we've been making computers until now, which is you put them in cement and you go
Right.
kiss them and go away. Now, if we really wanted to have something that was brain-inspired or nature-inspired, we would say, okay, the thing is going to constantly evolve,
Yes.
a little bit like the cloud now, and where it would be redesigning itself based on the problem.
That's right. And learning. I mean, this is
That's
where,
what learning is, isn't it?
yeah, it's all going to be, these computers are all going to be about learning. And you know, it's in the home now. I mean, you know, I just got Google Home. Many of you got the Alexa and from Amazon, and you train your voice. So it actually learns to recognize each of the voices in the family, and then in the cloud correlates that with your calendar and your email and your where you go to work and all of this stuff. It's very baby steps, but it is certainly going to be the driver. And this is where machine learning is becoming so important. And where all these Nonvon Neumann architectures are starting to be very practical. So Google made the executive decision it was going to put machine learning, and particularly multi-layer neural nets, in everything it does. And that meant that they were going to have to build like 20 or 30 new data centers, and I don't know, these are like $100 million data centers. But some of the Google engineers said, well, but you know, if all that is needed for is solving, say, TensorFlow, which is their open source version of machine learning that they've made available to everyone. Why don't we make an ASIC, make a specialized chip that just accelerates the computationally intensive part of the machine learning, and that's called a TPU, a tensor processing unit. And they did that, and it found out that they could just build racks of these things, and as a result, didn't have to build another 20 or 30 data centers. So it's billions of dollars of investment.
Yeah.
And it's much faster, and it's 100 times more energy efficient than the traditional way. And it was actually the use of those TPUs that was essential in beating the world's best Go master. So that...
Right. And now Intel's followed in their own
yeah,
way.
and Nvidia has, if you'll notice, the new Volta from Nvidia has a quote-unquote TPU in it. That's their design, not Google's design.
Right.
These are all Nonvon Neumann machines. And so we, having developed all this pattern recognition lab, one of the things that we've been doing lately is getting NSF grants to support our work at Cal 82 and the pattern recognition lab. And so I've talked to you before about the Pacific Research Platform, which is a $5 million grant that I'm PI for that takes all the West Coast research universities from the University of Washington down to San Diego, and takes the big data science researchers from particle physics to biomedical to earthquake engineering, and literally to their desktop, to their disk, survives about 1,000 times the speed of the commodity internet. Well, we're now just got a new grant to take 20 of the top, or 30 of the top machine learning faculty in computer science, not the application guys, at 10 of these campuses, Stanford, Caltech, Berkeley, down to San Diego and so forth. And they're all working on different kinds of machine learning, but they need to have GPUs to train on. And it turns out that if you go to the cloud, these are all double precision, expensive GPUs. The gaming GPUs, which they ship 50 million or so a year, Nvidia does, those are actually what they want, because the noise that's inherent in the data that you're actually learning on is such that doing it in double precision doesn't make much sense. But most people haven't got access to these for GPUs. So that we've got 256 of these that we plunked into these universities, and because they're on these high-speed networks, they all can act together as kind of a pseudo cloud. And so that's the von Neumann piece. But then we're our pattern recognition lab, as you heard 2 years ago, IBM's True North that you were mentioning is in the lab, and Dan Golden, who was here, was talking about New Edge, which is all very amazing Nonvon
And we
Neumann
have
architecture.
Bob Patty here this
Yeah,
week.
there's even something called Coventry Computer. I'll just skip by that. And we've signed an agreement with. And Xilinx, we actually have a top-level guy coming down on that soon. Qualcomm's going to provide a lot of the Snapdragons. They're going to have actually these things in the Snapdragons. So we're going to have all of these available. But then the thing that I'm really excited about is that because we can extend these high-speed networks out into, for instance, the NSF-supported double precision GPUs in case you need them, Amazon Web Services, which also has a lot of the GPUs, the TPUs, Google is now developing an academic program to make those available. I'm putting in a grant for a lot of researchers to make those available. Microsoft, which we've talked about before, has put FPGAs, field programmable gate arrays, Nonvon Neumann, in all their Bing servers and everything else. IBM, the Air Force lab, bought a 64 version of the True North, and then, of course, the big cloud that Dan Golden is making that he talked about here 2 years ago. So now imagine all of this around this thing, and all, 8 different kinds of machine learning, one of which is deep learning, and multi-layer neural nets are then gradually optimized across all these things. Then you have a laboratory to really begin to explore some of these beyond exascale models, and of course then get the applications on top of all this.
And I don't know if I should talk about this or not, you were thinking about...
It's a little late. Go ahead.
Expanding the PRP or the Chase to a national footprint.
Yes, we had a workshop in Montana State on the national research platform. So in other words, if we've got, say, 25 research universities and say there's 200 self-identified research universities in the United States, how do you scale this all up across the entire country? And in fact, it was born global. So we actually have collaborators we had here 2 years ago in Japan, in Korea, Australia, Netherlands, and so forth. All of which, by the way, can move at these 10,000 megabit a second to 100,000 megabit a second speeds across with very large data sets. And this is really kind of kindergarten in a way. I think where we're going to see is just so much more radical than this in literally the next even 5 years. 10 years, we won't even, it won't be recognizable.
And if you take, I think that you mentioned that would probably be the largest computer on the planet when you finish that project. When you, if you picture pictorial processing in this story, how does that fit?
Well, when you go back to the first supercomputer I was working on, it was 1 million floating point operations a second. So which of those 1 million 13-digit numbers that you just multiplied do you want to look at?
Right.
It was already a reductio ad absurdum to look at the numbers 50 years ago. And that's why I spent my whole career, bringing visualization into these capabilities. I'll talk later this week about using virtual reality to plan my own surgery. When my surgeon and I were in the cave looking at my large intestine about 6 feet high, we weren't looking at any numbers.
Yeah.
And the surgeon was, in her mind, instantly changing what she saw, all of which at the end was MRI. It was somewhere down the bottom were numbers. But she was instantly changing it into where she was going to do, how she was going to plan out the 5-hour operation. It was all visual. There was no numbers. And so the human brain is set up, a quarter at least of the neurons in your head are about vision. And so it's the natural way to interface with virtual worlds that have become essentially as high resolution almost as the physical world.
Yeah.
And so how we exactly get the computers to do that is part of why we're putting this in place. But a lot of it is is machine learning. When Google had this big thing to go out and find all the cat pictures on the, what were we doing when we invented the internet and the web to make the world safe for cat videos? So anyway, and they can, but just by doing machine learning, they could recognize cats, not dogs, and so there's the beginnings of this, but it's accelerating exponentially.
I want to go back to your surgery thing. This will happen. For those of you who are able to stay this whole week, you're going to see an amazing thing that Larry did. And when we were just looking at Chris's presentation and Valerio's, and you see this methane molecule, and we have someone here as a fire starter from Linked, and they're providing kind of global systems integration for CAD/CAM manufacturing. It used to be called CAD/CAM, now it's advanced manufacturing. It's not too far from your presentation later this week where you say, well, it's not just a matter of helping us see the thing, but someone's going to actually cut you in half and then do some stuff in there, right? And so, or however that worked.
Yep.
So the actual, not just seeing it, not just taking it to the brain, but then going back in, and it's not hard to imagine, I mean, in your case, it's just get the surgery right. But in fact, with other situations like molecular creation or something, it might be, well, this has this physical property, and I don't like that so much. I'm going to add one more atom here. And you could literally, in real time, be designing things which had abstract properties way up here.
Yeah.
And computing partly in your brain and partly with the system, and interacting with those two things and going back to effect change in the real world.
Yep. Maybe we should ask for questions.
Other questions? Very quiet crowd today. I don't know why.
You kept them
more
up too
coffee,
late.
more chocolate. I think we have somebody here.
Hey Larry, can you convince me that it's not too soon for us to start instantiating silicon architectures to match the limited knowledge we have of machine learning and the new style of things we want to do? I know we can't start too late. Convince me we're not starting too early because machine learning models are developing so fast.
Yeah.
We have the things we've been doing for 20 years, but we're also, the reason Azure uses FPGAs rather than custom ASICs is they change the model every week.
Right.
And you don't want to make new custom silicon every week, so you do it in FPGA. But if we're instantiating into something like North Star and the other things that are fixed silicon, how do we make sure we haven't done what seemed like a promising angle early on, and then when we get to it, it's like, oh, another 3 weeks of research and we went another way?
Well, I think it's a very good question, and I think it's just like life. It's evolution. And so the life tries a lot of different things and has been trying a lot of different things for about 4 billion years, and most of them fail, and that's just fine. And then you flush them, and then something new comes along. So I think this, I mean, look how complicated this is, and there's a lot more we added. It doesn't matter. I don't care who wins and loses. It's irrelevant to me. My only interest is getting as many diverse new architectures and as many different software techniques and as many smart people around the world working on these things as possible. And then it'll just boil. And it doesn't matter whether, you're not putting all your eggs in any one basket. And then the other thing, of course, is that life specializes. I'm fond of saying that on this planet, and if you look at the Milky Way galaxy, you got like 100 million stars, that's 10 to the 11, and you got at least 10 to the 11, 10 to the 12 of those galaxies in the universe. So the number of stars in the universe is like, let's call it 10 to the 22, 20 to the 23. That's like 100 million times fewer than the number of microbe cells we have on this little speck of dust, the Earth, in the little corner of the universe. So life really just tries everything. And that's sort of the spirit, I think, of where we're going. Yeah.
Larry, I'm curious, what's the prospects of moving away from a binary system towards a quantum qubit system? What would that do for heat? What would that do for capacity? What would that do for the future?
Well, we don't really know, but I do know that I just talked to the head of one of the most top executives at IBM. They say they have what they think will be the really breakthrough quantum computer architecture I talked to the same people, level people from Google. They say they think they have what will be the breakthrough Google quantum architecture. And of course, NSA and all their friends think they are going to get there. So these are very specialized machines compared to what we're talking about. But if a problem like, for instance, simulating some of the things we saw with Chris in this morning, actually simulating quantum systems, physical quantum systems, right? These things will be lightning fast. And again, I think we're so raised for so many decades that we got this general purpose computer, and it's going to do everything. And look at our smartphones, right? We got these, it's going to do everything. I think that's over. I think we're going to have a vast diversity. Now, it will be packaged, so as far as you, the poor human, dumb human, like, why do you have to know? It'll take care of it. And you'll be fine. You'll download more cat videos. But it will be under the hood a much more diverse architecture, and quantum will have a very important role and a growing role, both in quantum, by the way, computing, but also quantum communications.
We need to wrap it up.
Yes, sir.
We have hit our red light.
Okay.
Thank you, Larry.
Sure.
As always, terrific.